In section 2 of chapter 14, we look at the ANOVA table. When you obtain the regression from the previous example that is shown here, then you get the ANOVA report here in green, and the detail of what is behind this is, or the formulas are here in yellow on top. Let's look at the first result. The multiple standard error of estimate is a measure of the effectiveness of the regression equation. It is measured in the same units as the dependent variable, and it is difficult to determine what is a large value and what is a small value of the standard error. It depends on the unit and other factors. The multiple standard error of estimate is equivalent to the standard deviation of the errors. And the errors, if you notice in the numerator here, the errors committed in the regression equals the actual values of y subtracting the estimated values of y. And then you estimate or calculate the standard error of the estimate by just taking the square root of the MSC, which is shown right here. The MSC, remember, is a variance of the residuals. When you take the square root of a variance, you get a standard deviation. And that standard deviation is, in this case, 51.04, square root of 2605, and it's called the multiple standard error of estimate. And this is how you can estimate this. First, let me do this quickly. We have done it before. Data analysis, regression, the cost. This was done in the previous section. And then I select the first three independent variables here that were used before. Check labels. You see an extra variable garage here, but that is going to be introduced later. And let me get the output right here below. We can actually, and we can move it here. And my equation is here on the coefficients, as you may recall from the previous section. Okay, so I can estimate estimated values of y, or y hat, or estimated cost is just simply equal to the formula. In this case will be the intercept, which we want to be fixed, plus the following coefficient, L18, which we want to be fixed also, times the first, notice corresponds to temperature, times B2, the first independent variable, plus the following letter right here, let's fix it, times insolation. Insolation is C2, and then plus the following cell, let's fix it, times the following independent variable and final independent variable D2. So click enter and you get the estimated value of y for the value of 250. So when the actual value is 250, the regression estimates 259 approximately. So if we copy this down, then we get all the estimated values of y. So this will be y hat, and this is my y, the cost. Now I want to find the difference between, let me just put him as y minus y hat. What is that equal to? Oh, I'm sorry, I put the formula, so I need to just label it. And that is equal to A2 minus F2. That is the errors, or the difference between y and y hat. And it can be negative or positive because some values are above the regression line and some values are below the regression line. So for this is negative, this is positive, etc. So if you calculate a variance from the first formulas that we learned in the course, when you calculate the variance of a sample, you sum a certain value minus its mean squared. So each value you subtract the mean and you divide by a minus 1. And the standard deviation is just simply the square root of that. Okay, that's what we learned in a previous chapter. So here, that standard deviation can be just in Excel calculated as the standard deviation of a sample, STDEV, from G2 through G21. Well, this is my estimated standard deviation of the errors, which is the equivalent, the errors of the difference between the Y and the Y hat, cost and estimated cost. This is what I get using the traditional formula. And this value here, 5104, is the square, which is the square root of MSC, is my more accurate standard deviation of the errors. And there is a difference between the two because this one I divide by n minus 1. Since I have 20 observations, this is calculated from using 19 in the denominator. But if you can see here in the MSC, the variance, we obtain it by getting the sum squares, which is the same as adding all these errors squares, and divided by 16. So the variance that we get here is not obtained by dividing sum squares by 19. I'm sorry, by 18 in this case. I'm sorry, by 19 because we have 20 observations. N minus 1 would be 19. So we don't get the variance by taking this number divided by 19. We divide it by 16. Okay, so that's why we get a higher number here, 5104 versus 4684, but the concept is the same. This is the standard deviation of the errors. Okay, let's continue. And it's 5104. Now there's also in the results in multiple regression, the coefficient of multiple determination, or R squared. We just called it coefficient of determination in chapter 13. The characteristics of the coefficient of multiple determination are, as you may see, are about the same as what we said in chapter 13. It is symbolized by a capital R squared. In other words, it is written as R squared, R to the second power, because it behaves like the square of a correlation coefficient. You just take correlation coefficient, square it. It can range from 0 to 1, but I need to clarify the correlation coefficient is a concept that we use for 2 variables only. Now we have 3 variables in relation to a 4th variable, but it is conceptually the same thing, the same idea of finding an overall correlation between the variables on the right-hand side of the equation versus the left-hand side, the y. It can range from 0 to 1. A value near 0 indicates little association. A value near 1 means a strong association. It cannot assume negative values logically because it's a value squared. And it is easy to interpret because, for example, in our case, we obtain from the original equation, we obtain 0.804. That means 80% approximately, 80.4% of the variation in the dependent variable, in this case cost, can be explained by the variation in the independent variables that we selected, the 3 independent variables. Now the R squared is calculated as the ratio of 2 numbers, the SSR, which is right here, 171220, divided by the SS total. If you take the ratio of those 2 numbers, you get the same 0.804. So in other words, looking at the variation due to regression, what is called SSR, divided by the variation total, which is SST. We interpret the R squared as I told you before, as 80.4% of the variation in heating costs explained by the three independent variables. The remaining 19.6% is random error and variation from other variables that we do not include in the equation. However, as we add, as it says here, independent variables, the R square or multiple regression equation coefficient of determination becomes larger. So in fact, if the number of variables k and the sample size is n are equal, in other words, we're using as many variables, independent variables, as the sample size is, the coefficient of determination will be a perfect 1.0. The reason is because the the SS total, this value here, is never affected by the whether we have 1 or 2 or 3 or 5 or 200 independent variables, because it's just simply based on the difference between each value and the average of the dependent variable. So it's cost, the actual cost values minus the average cost. And however, as we add more independent variables, even if they are not very related to the dependent variable, the SSR will increase and increase to the point that it becomes 1 if we add enough independent variables to make them equal to the sample size. So due to this, there's another coefficient of determination called the adjusted coefficient of determination, which in the report, if you notice, is right below R squared. We have an adjusted R squared of 0.767. And that adjusted R squared is calculated as 1 minus the MSC over MS total. So I'm sorry. Where's the MSC? We know that the MSC is the number 2605.95.5. Let me just say 2605 right here is the SSE divided by 16. That's the MSC. Well, if we can calculate an MS total, it'll be SS total divided by 19. So we'll get another value here. Well, the ratio of those two value is the adjusted R squared. It adjusts for the number of independent variables, and it's not going to be equal to 1 if you just keep adding variables. It is adjusted by the number of independent variables, and it gives you a more accurate version of the correlation between the independent variables and the dependent variable. So when you calculate the adjusted R squared is equal to 1 minus MSC over MS total. 1 minus MSC, we know that it's right here, 2605.955, and divided by the MS total, which is a new calculation, is just dividing the SS total by 19, which is here in the denominator, okay? And you get 1 minus 0.233 is equal to 0.767, which is the adjusted R squared. And the interpretation is the same as the R squared. 76.7% of variation in heating cost, the dependent variable, is explained by the three independent variables. The remaining 23.3% is random error and other independent variables not included in the equation. And that's the end of this section.